Today we're going to look at ways to get energy that do not involve fossil fuels. Essentially, we're going to be looking at renewable energy resources today. And we're going to start by looking at fission. And these first two should hopefully be somewhat review from our units on atomic and nuclear physics. But fission, of course, is when we break apart a larger nucleus into smaller nuclei. It occurs when you have a stable parent nuclei. The most common for nuclear reactors is uranium-235. And remember that 235 is the atomic mass of that particular isotope of uranium, and it's bombarded with slow neutrons. We call them slow neutrons because they have to move slowly. If they're moving too fast, then the reaction will not occur. It won't hit the uranium. It won't break it apart. So they have to actually be moving kind of slowly, and that's part of why they're done in water. It actually slows the neutrons down so that the reaction can occur. That neutron actually becomes part of the uranium nucleus, and you end up with uranium-236, which is a much less stable nuclei. It then breaks apart into two smaller daughter nuclei and 3 neutrons. And this is what we call a chain reaction. You start with one neutron, you end up with 3 neutrons, which then go and hit 3 other uranium atoms, and so it's a progressive process. And because each fission reaction does release 2 or 3 neutrons, the reaction can grow exponentially, and this is the idea behind nuclear weapons. This is how they work and why they're so devastating. If this was allowed to continue, you would have an enormous amount of energy released in a very short period of time. When you start to have uncontrolled nuclear reactions, you get nuclear meltdowns, and in that particular case, the fuel rods, the nuclear material, actually gets so hot that they melt, and it sets the plant on fire. And as we said, that's also the idea behind our nuclear weapons. So, in order to control the reaction, you have to take certain steps. In order to control the speed of reaction, you use what are called control rods. Most commonly, these are materials like silver, indium, and cadmium that absorb, or that have the ability to absorb, free neutrons. And so what happens is, as the reaction occurs and multiple neutrons are emitted, a number of them are absorbed by these control rods, which allows the reaction to remain controlled. So instead of an exponential growth of reactions occurring, it occurs at a steady rate. And depending on the amount of the control rods that are in the system, you can speed the reaction up, slow the reaction down, and basically they can lower these control rods down into the reaction area or raise them up and have them in any fraction of the rods in the reaction area, depending on how fast they want the reaction to occur, how much energy they want to get out of it. As we mentioned, if the neutrons are moving too quickly, they'll pass through the nucleus without changing it, without binding to the nucleus. And so that's why we need these slow neutrons. And it's just one that has energy that's equivalent to a gas molecule at room temperature, which is approximately 1 electron volt. And in the reactor, you have what we call moderators that control the speed of these neutrons. In most moderators, it's water. Essentially, the water just slows down the neutrons as they pass through. And you've probably heard, especially when we're talking about weapons-grade plutonium, things like that, about something called enrichment. And in nature, most uranium deposits are primarily uranium-238. That makes up about 99% of the uranium that's found, that's mined from ore. That particular isotope is not fissionable because what happens is the uranium-238 will form plutonium-239 which isn't the same reaction that we want to have happen. It doesn't it's not as efficient, and so what they do is we add uranium-235 to the uranium-238, and so you have a mixture of isotopes within a particular fuel rod. And so you have primarily still the uranium-238, but then you also have it enriched with, or you have added to it, uranium-235, which helps to increase the odds of fission occurring. And it's a little bit different in mass, as we know, but that's okay. And one of the kind of recycling processes that's actually starting to happen more because the fuel rods are still dangerous even after they've been used. Afterwards, the fuel rods contain a lot of that plutonium-239. They're actually developing reactors that can use the plutonium-239 as fuel, and so now we're going to be getting, now you can get more out of a single fuel rod before it has to be stored in a radioactively safe area. Our power plants, our nuclear power plants, really work in a very similar way to our coal-fired or our natural gas or any of our fossil fuel power plants. You have some source of energy. In this case, it's the fission reaction, which heats up water. The water turns to steam, and that steam turns a turbine. Now, the difference, or the primary difference, one of the big differences here, is that in a nuclear reactor, we have to have two separate water systems. And what you have here, the control rods of the nuclear reactor are here in this middle area, the pink area. That water in there gets heated up from the reaction and pumped through these pipes. And the water that gets heated up by that reaction actually then goes into another water containment system, and the pipes heat up, and the pipes then heat the water in this secondary system over here. And the reason for this is because the water that's in direct contact with the control rods and with the fuel rods, and that it comes from the reactor, can become dangerous itself. It can become radioactive itself. And so they want to keep that as confined as possible. And so you actually have two sets of water. The initial set gets pumped through here, heats the secondary water, which is what turns to steam. That steam gets driven through our pipes and forced through the turbine. It turns the turbine. Once it passes through the turbine, it's cooled off some once it passes through the turbine because it's transferred a lot of its kinetic energy into the turbine. But then you have a condenser, which is basically cool water flowing through a pipe that cools down the steam until it turns back into liquid water, and then it gets pumped back up into the water containment tower, or into the water containment system. And now within the fission power plant, we have what's called a heat exchanger. And this is kind of what we just talked about. The water is heated by the water that's heated by the fission reaction, expands through the pipe, spins the turbine, and then it gets turned back into liquid water to repeat the process over and over and over again. If we were to take a look at a Sankey diagram for a nuclear reactor, it would look something like this. They're roughly as efficient as our fossil fuel plants. If we look at it in terms of 100 units, so 100% of the energy, about 30% actually ends up coming out as actual useful electrical energy. You have some that's lost to friction. A lot of it gets lost to the cooling towers. And this is where we lose most of our energy in most of our systems, is to thermal energy. The steam, as it gets pumped to the turbines, doesn't transfer all of its kinetic energy. A lot of it gets pulled out from the condenser coils and carried out to the cooling tower after it's already passed through the turbine. And so you lose most of your energy there. Some of our issues with nuclear reactors, and the reasons that they're not more prevalent, although we do have many of them in the United States. There's always the fear of thermal meltdown. If any of the systems go down, the reaction gets out of control and the fuel rods melt, light everything on fire. It's a bad situation. Nuclear waste is a very big concern. The half-life of the waste that comes from a nuclear power plant is thousands and thousands of years, and so we have to store those spent fuel rods somewhere for that time period until they become stable, until they become safe. Most of the time right now they're stored in deep underground bunkers that are lined with lead and other materials to keep the radioactivity in. Finding the uranium for the fuel source is an issue because the best deposits are really still only about 1% uranium, so there's a lot of cost involved with the actual finding and mining of uranium. And then the stuff that's mixed in with the uranium, because it's mixed with uranium, becomes radioactive. And so you have a lot of dangerous extra stuff that's left over from the mining that you're pulling out of the ground. And then one of the stages of decay of uranium is radon, which is a toxic gas. And then there's always the fear, of course, that the nuclear material could be used to make weapons. Not so much in our country, but certainly in some of the other countries. Or that our waste uranium could be sold or could be used by people to make weapons. Then we have fusion, and fusion is, of course, the opposite of fission, where fission was splitting apart larger nuclei. Fusion is joining together smaller nuclei, hydrogen and helium atoms, to form larger nuclei. And as we hopefully remember from, again, our previous units, the amount of energy available in a fusion reaction is many, many, many times that of a fission reaction. The problem is getting the reaction going and keeping it going. In general, the fusion that we create on Earth or that we do in labs is between a deuterium and a tritium nuclei, whereas on the Sun it's primarily just single proton hydrogen nuclei. And so in our deuterium and tritium, we see at the upper left here we have our deuterium, which is a proton and a neutron. One proton, one neutron. Tritium is one proton and two neutrons, so atomic number or atomic mass of 3, atomic mass of 2. The fusion reaction occurs. We get our helium atom. Okay, so that's 2He2. That should be an E. And then we get a neutron left over. And then, of course, a significant amount of energy from the reaction. And that energy is roughly 3 to 4 times as much as fusion. It's also much, much cleaner. There isn't the radioactive waste because we're not dealing with radioactive material. But similar to fission, there's no carbon dioxide emitted. So both of these have the benefit of not releasing harmful carbon dioxide into the atmosphere. Fission, of course, does have the nuclear waste, though, so there's that aspect of it. With fusion, it currently takes more energy to actually get the reaction going and keep it going than we're getting from it. And that's because of the extreme heat and pressure that the reaction has to be under in order for it to actually occur. You have to get the deuterium and the tritium to almost 1,000,000 Kelvin. You have to turn it into a plasma, and the reaction currently isn't sustainable. We're starting to make a lot of strides towards sustainable fusion reactions, but the technology isn't there yet. You may hear the term cold fusion. And when we talk about cold fusion, we're talking about fusion reactions that are occurring at significantly lower temperatures than this 1,000,000 Kelvin. When we're talking about cold fusion, it's not in reality cold that we would think of. It's still very, very hot, but compared to the temperatures that we're working with now, it's much, much cooler. And in order to confine this, scientists use electromagnetic fields. They use what are called tokamaks. Here's a couple pictures of them so you can kind of see what they look like. But in these, because the plasmas are so high energy and the temperature is so high, you can't contain them in a normal container. You can't just put it into a beaker and let it go. You have to use a combination of electrical and magnetic fields to maintain the plasma.